You put a chocolate bar on.
Okay, we're on. All right, today, first we're going to go over a couple of problems from the homework. So, the last one was 34. Some people had some trouble with on page 583. So page 583. Yes, we'll have time for one or two of these, but that'll be about it. Okay, so number 34 said 3 plus I over 2 plus I squared. And the quantity was squared. Now the goal for all of these is to get this to somehow look like A plus BI. That's why I was telling you guys to separate into two fractions before. You really want to separate out the real and non-real components of your complex number. So in this case, the first thing you have to do is FOIL, which gets you 4 plus 4i plus I squared. Is that correct? Which means you get 3 plus I over, what's I squared going to be? I squared is the exact same thing as -1. So we combine the 4 and the -1 to get 3 plus 4i comes along.
Gosh, just did I.
Is that an acceptable way? I know, then the answer would be 1 would be golden. Is this an acceptable way to leave your answer? No, now we have to perform the indicated division. Did I teach you a way to actually divide complex numbers? No, not really. It's a cheat, but we'll go ahead and do it. As we talked about last time, now you multiply top and bottom by the complex conjugate of your denominator.
Oh, you mentioned that, but I don't think you really did it.
We did it. It's just this is not, this is what complex division is. My point being, they're really, complex division doesn't look like any other sort of division. It looks like multiplication.
There's no actual division.
Let's just say this works. And stick with this for now. Okay, so I have to FOIL the top, which will get me 9 minus 12i plus 3i minus 4i squared. It looked like on the homework some of you guys forgot the I squared at the end of some of your problems that involved expanding foiling. Now on the bottom I have to FOIL, but I know I have A plus B, A minus B, so I already know my answer is going to be A squared minus B squared. I can FOIL it out and show the steps, but that's the whole point of the complex conjugate. We choose this method because it always makes the two middle terms disappear, leaving you, in this case, with 9 minus 16i squared. I squared, once again, is -1 everywhere it shows up. Yes, on the bottom you're going to have 9 plus 16, or 25. On the top you're going to have 9. Well, no, you got 9 plus 4 times -1, or minus 4 times -1, excuse me. So the I squared makes it 9 plus 4. So that's 13 minus 9i. And because we always want to distinguish between the real and non-real component, this is mathematically correct, but we would always write this as 13/25 minus 9/25 I. And then you'd simplify each one separately as needed. Yes, sir?
I got the exact opposite.
Did I make a mistake somewhere? Double check me.
No, I mean I got -13 plus 9.
I don't see an obvious mistake I made. If you see one,
No, I mean I made mine -3 plus 4i instead of 3 minus 4.
oh, that shouldn't have worked. Oh, interesting. So wait, did you get?
I got all the same steps.
Did you get -13 and plus 9i on the top then?
Yeah.
Okay, so when you did -13 by -25, this became positive. And when you did, should have been when you did plus 9i minus 25, that should have became negative. So if we both were headed for this form, you should have gotten here in another step or two. Does that make sense? You should have wound up with a negative divided by a negative here. So you did the complex conjugate slightly differently, but got the same answer. Awesome. There's nothing wrong with that. Any questions on this one? I like this one because it covers literally everything I talked about on Friday. You can combine i's as like terms. You can combine the real components as like terms. I squared is -1, so minus something with an I squared is going to become addition. This covers your addition, subtraction, multiplication, and division of complex numbers, all in one example. I like this one.
Really?
Any questions before I erase it?
No.
Nope. Okay, Danny, you asked for number 28, and then
Yeah.
we'll go on to something new. Okay. 28 said,
Can we do 24? Yeah.
Pardon?
20, or what are we doing?
28.
And can we also do 24?
Maybe at the end. I'm not sure if time for 24. No, 24 would be a good one. Hang on, let me see how quickly this goes. 28 said to write a quadratic equation with the solutions plus or minus I, right?
Yeah.
Okay. Well, remember, when you get to the point of solutions for a quadratic, it's usually because you factored it and set it equal to 0. That's one of the ways to get the solutions, correct? So if x equals I was one of the solutions, that must have come from x minus I. And if x equals -I was your other solution, that must have come from x plus I, correct? Any questions on that? So if it says write a quadratic equation with these solutions, you must have had these as factors. What equation has these as factors? I don't know, let's FOIL it. X squared. What's going to happen with the middle terms? I'm going to get plus I times x for my outer, minus I times x for my inner, minus I squared. What happens with my middle terms?
They cancel out.
They cancel out, which if you see you have a minus b times a plus b, you could have anticipated that. So now I get x squared minus I squared equals 0. Does this look like your usual quadratic equation? Did you do quadratic equations with complex numbers in them in Algebra 1?
1
Probably not.
or 2?
In 2 you should have.
Not in Algebra 1.
Not in Algebra 1.
That was,
That becomes x
that was
plus
too
1,
long
right?
ago.
This becomes x squared plus 1 is my point, equals 0. And you should remember in Algebra 1 and parts of Algebra 2, you were told this had no solutions.
Oh, but it does.
It does. 2 complex solutions. It doesn't have 2 solutions on the x-axis.
So he lies to us. They just
No,
make
you
it
probably
like
just didn't
To make it
teach that.
simpler.
Well, the correct phrasing is, the honest to God correct phrasing is this has no real solutions.
that. No.
But Algebra 1 and Algebra 2 teachers, we can't remember to say real every time. So we just say it has no solutions. I sometimes remember to say it has no solutions that you need to worry about, but in 2 or 3 years you will. But,
That's 2 or 3 years ago.
Yeah.
2 years ago.
yep.
2 or 3 years ago. Yeah.
But 2 or 3 years from now you will. Thank you. And then I said something backwards in that sentence.
So 2 or 3.
So this is your quadratic that has these 2 solutions. It's not the only one, but it's the only one we're going to care about. That's number 28. You guys asked about number 24 because it had the radicals. I will do that really quickly and then go on to what we have to do today. 2 plus root 3 times -1 plus.
-12.
That does require you to remember what I really is. Let's FOIL it. -2 minus root 3 plus 2 root -12 plus the square root of -36. Remember, I can multiply under a radical if they're both square rooted or cube rooted or whatever they are. Now let's break this down a little bit. I've got -2 minus root 3 plus 2 times square root of -12 is -1 times 2 times 2 times 3. That's my prime factorization, right? Okay? And this plus 36 is going to be square root of negative 1 times 2 times 2 times 3 times 3.
Which is just 6 and 6.
4 times 9, 6 and 6. A couple ways you can do this. I'm a big fan of going all the way back to the prime factors.
Would it be 6 on
Yeah, this is going to be kind of neat. So what we have here, negative 2 minus root 3. This one is going to be plus 2. One of these 2's can escape. Square root of 3 will still be there. And what's another way to write the square root of negative 1? And this one,
Wait, Mr. Bella.
yes sir.
It's root negative 3 multiplied by root negative 12, right? To get root 36? Or root negative 36?
Yes, 3 times negative 12 is negative 36.
Oh, it's positive root 3. It's root positive 3, not positive.
It is root negative 3.
Because I was going to say it should be
Thank you, I miscopied that.
negative. It should be
Negative.
positive 36.
Negative.
Because there's.
Nope, that stays negative.
There.
Thank you, Danny. I was rolling right along for the wrong type of problem. Okay, so that's negative. That stays negative, that stays negative. And the only other difference is
the bottom.
this becomes positive, right?
The bottom, yeah.
Okay, so we're still good. So this just becomes, this is still 2 times 2 root 3i, correct? And then this is just 6. So that one was a lot easier than I thought. Is that correct now? And this one, which I haven't been dealing with, is negative 2 minus positive root 3i plus 4 root 3i plus 6. Negative 2 and 6 are like terms. Minus 1 root 3 plus 4 more root 3 should get me plus 3 root 3i. And that should be the answer. Sorry about that, that was more confusing with me not noticing that it was a negative 3 when I copied it from the book. Any questions on that one?
Can you take a picture?
Yeah.
Oh, we're recording.
We're recording it, yeah. I can also get a picture, just in case you don't want to go through the whole video since I'm not recording from my phone. That's a good one. I'll just go ahead and have them both in the picture. And I'll email that to you guys when we're done. Okay, new stuff. Now we really have to get going. New notes. We're going to combine two of your guys' favorite things, complex numbers and polar coordinates.
How did you know my favorite thing?
These are a few of your favorite things. Okay, polar form of complex numbers. There is a, if you make a leap of imagination and you remember your unit circle well, these aren't bad. They're really not. Now, you have to remember some geometry. And in some ways, these are easier than what we've done with other complex numbers. We'll start talking about that tomorrow. But for now,
What have we done?
pardon?
What have we done with other complex numbers?
Add, subtract, multiply, and divide them.
And so,
You don't want to add and subtract these. Multiplication and division. We'll go over those tomorrow. There's a couple of options with that. Okay. Here is a complex number, 1 plus, actually I'm do this a little differently. Looks like the way I draw it. Square root of 3 plus I. Square root of 3 plus I. It's a complex number. It means on my positive x-axis I went to root 3. And it means I went up 1i. Now in the complex plane, there's a lot of geometry that still works. Some of it gets weird, we'll talk about that tomorrow, but you've still made a right triangle by going up to any complex point. similar to how it works in the rectangular plane. But again, remember, in a rectangular plane, you have the number x and the number y, two different numbers giving you a two-dimensional point. Here you've got one number with a real component and with, as we talked about last Thursday, its necessary complex component. If you have real numbers, their negative square roots have to appear perpendicular to your number line. Okay, tell me something about the triangle I've drawn.
Triangle.
That's segmentation.
What about it?
36.
Yep, it's a 30, 60, 90 triangle. Because I've drawn 1 unit high, 30 degrees. I've got a root 3 side, that'll be opposite to 60 degrees. How big is the hypotenuse? 1 to root 3 to... well, okay, just let's go with distances. Don't think about the I part yet. Just 2 for now, yeah. It is a distance of 2 from the origin. If we were doing this in polar form, if this were the point if this were the rectangular point, root 3, comma 1, then this would be the polar point 2, comma 30 degrees, correct? Okay, the problem is that comma. See, like I said before, the polar point, square root of 3, 1, that is 2 different numbers. So if we want to represent that in polar form, yep, we do that for r theta. But we can't use that comma here because we're not talking about 2 different numbers. We're talking about 1 complex number. So we need a slightly different way to represent that. And we can use what we know about polar coordinates to help. One way to talk about the square root of 3. See, I want to talk about, let me go back a step. I want to talk about r and theta, but I want to describe this point, but I don't want to use r and theta to describe it. I only want to use my hypotenuse and my angle to describe it. Okay?
Isn't that r theta?
Yes, but how do you specifically describe this? How do you describe the adjacent side of a triangle in terms of the hypotenuse and the angle? How do you write that? How do we write it for
Cosine.
Cosine? What specifically x? I know, I'm making it sound more confusing than it has to be. In the jump from rectangular to polar, what was x? What was that conversion?
It was 2 theta.
Close? Okay,
Oh, you
in
had-
general.
Oh, r cosine theta.
Our cosine theta. And what was y in general?
I
Okay.
thought you meant like the...
Right, I know, for this one.
No, for the charts that we did. Like,
Oh, right.
R was y.
Now I know what you're talking about. Yeah. Okay, no, not like that. I know I'm not expressing this quite as clearly as I'd like to. So this is for polar. This is for polar and rectangular with normal numbers. Now we're on the complex plane. Let's go back to the complex plane again. Now what you're going to get here is you have a plus bi. Now, the a part, that's similar to your x. It is actually your x because it's on the x. It's on an x-axis. X was r cosine theta, so your a part is also going to be r cosine theta, where r is, again, the length of your hypotenuse. But now we're not going to do a comma. Why? We have to do plus. B is a lot like your y. And y was r sine theta, and it still is. But we don't just have b here. We have a plus b times I. So I can take the a and replace it with r cosine theta, take the b and replace it with r sine theta, and the I just comes along for the ride. So I take this complex number, and to write it in polar coordinates, I get r cosine theta plus r sine theta I. I'm going to do a tiny bit of algebra before I go on. We usually write this, we factor out the r, and then we write cosine theta plus I sine theta. It is still the same thing as A plus BI. We've just factored out the R and moved the I to the front. Does this freak anybody out? You guys okay with this?
For the sake of
For the sake of moving along, we'll pretend it doesn't.
So if you plug in R and theta into that,
So yeah, we can plug R and theta into this, but there's one.
where does it get you?
We'll go. That will go more into tomorrow. But there's one more abbreviation I want to use here. I grew up with this abbreviation. I used it in college. I don't think your textbook has it, so this is the only place you're going to get this. This is then abbreviated further to R cis theta, where CIS stands for cosine plus I sine.
CAS stands for what, I'm sorry?
Cosine plus I sine, CIS. So going back to this specific example,
What's the IS prime investigator?
that's CSI.
Oh,
two dropper.
Don't mix this up with CSI, please. So root 3 comma 1 went to 2 comma 30. Root 3 plus 1 plus I is going to go to 2 cis 30 degrees. This is the polar representation of this point. Tim can sharpen for a moment while we ponder this.
How do you possibly sharpen?
Now, anyway, so instead of 2 comma 30, we get 2 cis 30, standing for 2 cosine 30 degrees plus 2 sine 30 degrees times I. That's how you change your A plus BI into a polar complex number.
What is going on?
Instead of talking about the adjacent and the opposite, we talk about the hypotenuse and the angle. This gets easier with examples, but it always starts out confusing. And you got to remember all of your special triangles and your unit circle and all that fun stuff.
All two of the special triangles?
Yes, both of them. In all 4 quadrants, though. Making, it actually works out to 3 per quadrant if you look at it. Because you got a 30, 60, 90, you got a 45, 45, 90, and then you got a 60, 30, 90. It's actually all 12 of your special triangles, but really all I have to do is remember one of them, one of each. Can I erase this now? I think you guys still have questions, but I don't think this is going to answer them anymore. Let's do a couple of examples. If I talk about the complex point, let's see, 5 root 2 plus 5 root 2I. There are a bunch of ways to picture this. Several ways. I'll start with an intuitive way, and then we'll start figuring out some strategies that work best with you guys. First off, what quadrant is this in? Not meant to be a stumper. Everything's positive. It's in quadrant 1, right? Okay?
Well, is everything positive? Does it have the I?
Good, well put. All your coefficients are positive. So you're still going to be in quadrant 1. You're going to go, this is a point 5 root 2 over and 5 root 2I up.
Yeah, whatever 5, root 2I be negative. Root 2I.
No, you're thinking about the, there is a positive I-axis and a negative I-axis. And this is a positive I-axis, even though it is the square root of negative 1. That doesn't change the sign of the complex plane can be weird is the short answer to that. That's actually a great question, Diego, but answering it won't help us with what we have to do today. So
when we don't get a easy triangle, then we have to use
calculator or something.
cosine.
Yeah, you have to get a little bit crazy, or pull out a calculator. We're going to stick to unit circle ones for most of this unit. What angle is this?
45 or
45 degrees. You guys know that why? Same vertical, same horizontal, same vertical, right? It's making a 45-degree triangle. All right, so that part's easy. What's that distance? If this is 5 root 2,
Times root 2.
let's go back to geometry. You have x times root 2, right? So if you know the legs of a 45, 45, 90 triangle, to get from the hypotenuse, you multiply by square root of 2. 10. So we know theta is, I'll switch to radians now, pi over 4. And Tim said it first, we know the radius is 5 root 2 times root 2, which is 10. So we are looking at the point 10 cis pi over 4, which instead of telling me go 5 root 2 over and 5 root 2 up in the complex plane, it tells me, like a polar coordinate, aim myself 45 degrees and go 10 units out. Does that idea make sense? Okay.
Is there a reason why you did it in radians? Or is it just because you wanted to-
I don't want you guys to forget radians. I'm going to switch back and forth. You guys still need to be good at them. Plus, as I've said a million times, I like them better. I have a crazy way that helps me remember this. I don't know if this is helpful for anyone but me.
Probably not.
Probably not, but we'll take a look at it anyway. If we're doing this without a calculator, then you're pretty much either going to see root 2s or root 3s, right? Unless you're looking at a point on one of the 4 axes. Because we're going to stick to 30, 45s, and 60s. So everything's going to be 1/2 root 2 over 2 or root 3 over 2, positive or negative, right? If you see root 2, what should that make you think of? 45, 45. So in my brain, I'm offering this as a strategy, not everyone's favorite. In my brain, I know I would like I'd like to look at a root 2 over 2, because that's going to be my cosine theta, plus another root 2 over 2 times I, because that's going to be my sine theta times I. Okay, so that way I know I'm looking at the cosine of pi over 4 and the sine of pi over 4. What would I have to multiply root 2 over 2 and root 2 over 2 by to get 5 root 2 and 5 root 2? I want there to be a 5
10.
here. I'd have to multiply by 10. So I know I'm looking at the cosine of pi over 4, and I know I'm looking at the sine of pi over 4, and I know that this has to be the same angle in both cases, because we're only talking about one angle, split up between these two terms. And I think, okay, I've got root 2 over 2, I'd like there to be 5 root 2. Well, if I had a 10 out here, that would get me that. So I am looking at 10 cis pi over 4.
This is just how you remember everything.
That's how my brain goes with this. I don't recommend that for everyone. If not, you might have to draw the special triangle. If not, you could pull out the x equals r cosine theta, b equals r sine theta. Conversions from polar coordinates, those would still work. There's a lot of strategies here that you can use.
Don't erase it.
Not erasing it. May I erase the drawing?
Oh yeah, you can erase it.
You can erase everything.
Alright, I'll start a new one over here.
New example.
New example. Let's look at, I get a good one from the book that isn't. And then we got to go backwards
Oh,
with some of these.
I missed.
That's okay, just don't sweat it. Okay, we're going to start this one my way just because we can. If you see a root 3 in there, are you looking for a 45-degree angle? Is it root 3? No. I mean, if you don't have a calculator in your hand, you're looking for exact answers, I'm only going to give you 30, 45, 60 reference angles. So let's see what we're looking at here. Root 3, we're thinking that's like root 3 over 2. Okay? If you don't see a root 2 or a root 3, well, this has to have the same denominator, so that has to be negative 1/2. What would I multiply times 1/2 to get 8, and by root 3 over 2 to get 8 root 3?
No.
16. It's always going to be twice whatever your common coefficient is if you have one. There are some snags to this. This does get more confusing than it's worth on a couple of these, but it works well for the simpler ones. What angle has a cosine of negative 1/2 and a sine of positive root 3 over 2, same angle on the unit circle? What quadrant are you in, first of all? Second quadrant, 2. Between 90, so you're either looking at 120, 150, or 135. 120, yeah, because it's a reference angle of 60 degrees to get the 1/2, and a sine of 60 degrees to get that. So we're looking at 120, which is 2 pi over 3, right? Okay, so it looks like we are looking at 16 cis 2 pi over 3.
You need me to graph it.
Pardon? Not if you're good at this little trick I just showed you. If some of the homework will say to graph, then you have to. If you didn't like that little trick I just did, then you have to go back to here and say, okay, if I go negative 8 over positive 8 root 3i up, make that rectangle, turn it into a triangle, so that's basically 8 root 3. Then you have to realize you're looking at an 8 root 3, 16 special triangle, where that's a 60-degree angle, so your standard angle is 120. And then you'd have to get 16 cis 120 out of this. If you hate that, there's more.
No.
But it's kind of a pain. If you use the conversions, they're kind of a pain. But they also work. You guys think you can handle it, either of these two strategies?
Maybe.
Maybe. Recognize the special triangle.
Correct.
They do take practice. And yeah, you got to keep your unit circle handy, Diego. I know you never go far without it.
I sleep with it, Mr. Bella. Right.
You should.
We'll eventually see them.
What's a little bit trickier is...
Listen to them.
I wonder if that would work. What's a little bit trickier is the polar back to rectangular. Actually, I think it's a little easier. Depends on, well, let's see what you guys think. If I say you're looking at 7 cis 3 pi over 4. Now I'm going to change that. Make that 5 pi over 4. What quadrant am I in? Tim, you're going to want to practice without your calculator.
Third.
Pardon? Third. You're in quadrant. How come you know you're in 3? What angle is that?
270.
I like how you're doing that. 270 minus 45. 225. 225 degree angle. Here's what I think Robbie did. He figured it's 5 45 degree angles, right?
I just did 2 times 2.
Awesome. So that's one way I would picture this is that's one 45 degree angle. Another 45 degree angle gets me to 90. Another 45 degree angle gets me halfway through quadrant 2. Don't even care what the number is. A fourth 45 degree angle gets me to 180. A fifth creates a 45 degree reference angle down here in quadrant 3. And then all I have to think about is what's 180 plus 45 or 270 minus 45.
Or you have 25% chance of getting the guess right.
There you go. So that's 225 degrees. Now since it's a 45 degree reference angle, the sine and the cosine will both be root 2 over 2. And because it's in quadrant 3, they'll both be negative. Awesome, because it's 225. So what we're looking at definitely is 7 times Remember, this actually means 7 times cosine of theta. This means 7 times cosine of 225 plus I times the sine of 225. So it's literally 7 times negative root 2 over 2 plus I times negative root 2 over 2. So I'm looking at, I forgot my equal signs, negative 7 root 2 over 2 minus 7 root 2 over 2I. 45-degree angle ones are fun because you're looking for the same number here and here, though they can have different signs. One can be opposite, one can be negative. Any questions on this idea? I think going back from polar to rectangular is actually slightly easier.
And you're about to see.
All depends on what you know better, your unit circle. If you know your unit circle really well, you don't really have to think on this. Here, I don't know, I always find myself having to picture the special triangle or the unit circle really well. All you're going to do tonight is convert. Tomorrow we'll do operations with polar complex. Probably have a test Friday on this chapter.
Next Friday?
Yeah.
Yes, tomorrow gonna be the last day.
Nice, do we have no homework?
No, stop. Hold on. Don't get excited yet. I'll know tomorrow for sure, so don't speculate now. Your homework tonight, however, which I will not erase this yet.
3-day weekend.
Oh, yeah.
Yeah, it is a free day. Is the market going all right?
Thank you.
Are you like a
Page 590, and guys, for what we're doing tomorrow, you need to be good at this. You must have practiced this homework. If you don't practice this homework,
You're screwed.
tomorrow's just going to be,
It's gonna
Yeah.
suck for you.
One of the nurse day,
kind of. 26 through 42 even, page 590. It's converting complex numbers to polar form, and then it's graphing complex numbers and writing them in polar form.
Sounds fun.
I would think so. All right, hang on one sec till I turn this off.
Bye, Nate.